Hi, welcome back to Chemical Engineering Statistics. Now that we have become acquainted with discrete probability distributions, in this segment we will briefly review the continuous probability distributions, which for the record you will encounter more in chemical engineering. The continuous probability distributions are often expressed by means of a probability density function or PDF. Probability is expressed by a number of geometric distributions parameters. The sketch on the right depicts a probability density functions. We cannot read the probability value directly from this curve, but we must integrate the PDF functions fx within certain limits. For example, the probability of a random variable x being between a and b is the integral of fx dx with the integral limits a to b. So it is the area under the curve that represents the probability. Another feature of the PDF is that the total area under the curve is exactly 1, which means that as in random sampling, we will definitely get one random x value. Now let's look at some of the continuous distributions that are often found in engineering. The best known continuous distributions is of course the normal distributions or the Gaussian distributions. This distributions is in the form of a symmetrical bell which is controlled by two parameters, mean or we call it mu and standard deviations, sigma. The normal distributions follow the empirical rule 68, 95, 99.7 as shown below. That is, the probability that x is in the plus minus range of one standard deviations is 68%. If this range is extended to 2 times sigma, then the probability becomes 95%. And if it is expanded again to plus minus 3 times of the sigma, it becomes 99.7% or almost 100%. We can get an infinite number of normal distributions because we can set any value for the mean and standard deviations. However, if the mean is set or standardized to 0 and the standard deviation is set or standardized to 1, then what is obtained is a very special normal distributions. We call it standard normal distributions, or also known as the Z distribution. The normal distributions of any random variable x can be standardized using the formula. The Z distribution table is one of the standard appendices of statistics textbook. Here we can see two examples of copies of two different books. The numbers in the body of the table represent the probabilities. The leftmost column represents the value of the z variable to the first decimal, and the top row represents the second decimal of the z value. When using the z distributions, please pay close attention to the basis of the integral for calculating probabilities, or you can see at the picture above. Does your book integrate from 0 to z, or from minus infinity to z, or else? This is very important to avoid calculation errors. Here I give two examples of simple calculation using z-distribution. The first question asks you to determine the z-value which result in a one left-sided probability of 12.3%. You just have to find the probability number that is closest to it, then read the z-value to the first decimal in the left column and the second decimal in the top row. The answer is minus 1.16. The second example is to determine the probability of getting a z-value greater than 0.85. Please refer to the explanation on this slide for your own practice. Some other continuous probability distributions that are also widely used are the log normal distributions and the t-distributions. The log normal distributions is formed when the logarithmic value of the random variable x is normally distributed. Meanwhile, the t-distributions has a very similar shape to the normal distributions, but is controlled by one more additional parameter, which is the degree of freedom. The lower the degree of freedom, the wider the form of the distribution is. Meanwhile, if the degree of freedom approach infinity, the t-distributions becomes identical to the z-distributions. We will use the t-distributions a lot in statistics. I close this segment with a few examples that show how pervasive this continuous probability distribution is in our life. For example, the environmental temperature anomaly is shown to follow the normal distributions. The size of the aerosol particulates in the atmosphere follows the log normal distributions. The example at the bottom right is a control chart, and this diagram is very useful for detecting deviations from the control state, which is indicated by the exit of the process behavior from the normal distributions. Of course, there are still many random variables around us that follow similar behavior. See you in the next video.